So here's an overview then of what we're going to talk about in this section. I'm going to start with just a description of what experiment design is, and put our the particular flavor of experiment design that we're interested in here within the context of various other sort of challenges that fall under the broader banner of experiment design. We're going to focus on a particular tool for experiment design, which is the Fisher information matrix, from which we'll derive various optimality criteria and then kind of see those in action in first linear models, linear least squares problems, and then we'll think more generally about non-linear models. I'll work through a sort of brief example using a medical imaging example, this time using a different modality that we haven't come across before, and then finish off just by talking about a couple of variations of the problem and trying to place this idea of experiment design within the broader modeling pipeline of, well, the kind of pipeline of designing and implementing model-based imaging applications. Okay, so just to start with the problem statement then. So up to now, we've been thinking primarily about trying to, first of all, estimate unknown parameters, and then also think about quantifying their uncertainty and possibly even selecting between different sets of parameters associated with different models. But through all of that discussion, we've assumed that we've given a set of measurements and the corresponding device settings from which those measurements were acquired. This experiment design, which I'm going to call Psi, the set of device settings corresponding to our K measurements, up to now we've assumed that have been given. But as we've seen, we've touched a couple of times on the fact that actually the quality of our parameter estimates can really depend quite acutely on the choice of this experiment design, the set of device settings or independent variables that we choose to associate with our measurements. And also, of course, by definition, these are things that are very much under our control. We can choose at what ages to measure our child's height, or what settings to put the knobs on an MRI scanner to before we make any measurements. And so the focus of this section is about how we make those decisions about the set of device settings that we choose for the particular set of measurements that we do, and how we go about making that decision. So one sort of way that we might go about it, just focusing on a single unknown parameter for the moment, is that we might try to identify the experiment design, the set of the CSI, or the set of independent variable settings that minimize the standard deviation of our parameter estimates, or in other words, maximize its confidence, subject to some additional constraints, such as the parameter estimates are unbiased. So over a large number of trials, on average, we get the true parameter value. We're also typically subject to some constraints on the experiment design itself. So there might be some constraints inherent in the measurement. We'll come back to that a bit later. But the key constraint on the experiment design typically is that we're given a budget of a number of measurements that we can make. And typically that budget will be that we're limited to some number, let's say big K, using our usual notation. So we're limited to a set of big K measurements. And obviously, if we didn't put that limit in place, then the answer to what's the best experiment design is always, well, we just acquire an infinite number of measurements. The more measurements we've got, the more information we have to base our parameter estimates on, and so the better our estimates. But when we're given a limited budget of, say, K measurements, then the choice of those particular measurements becomes very crucial. So our sort of general strategy for this then is we will assume an unbiased estimator. I think that's reasonable to do here because the bias in an estimator isn't generally to do with the experiment design. It would be more to do with choosing the wrong noise model or objective function. So we'll assume that our our estimates of model parameters are unbiased. So on average, over a large number of trials, we would average out to the correct answer. And then we're going to try to quantify the standard deviation of each of our maximum likelihood parameter estimates as a function of the experiment design, as a function of the set of device settings that we use to acquire our measurements. And once we've done that, we can then we've set ourselves up an optimization problem, which allows us to search for the combination of these Ys, these device settings or independent variables that minimize these estimates of the standard deviations of our parameter estimates, or in other words, maximize our confidence in those parameters. So as I said at the start, a key tool in that is this object, the Fisher information matrix. So its definition is that there on the slide, and I'll come back to that in a second. But once we've estimated it, its inverse is the expected covariance on our parameters. So exactly what we said that we needed on the previous slide. So let's look at this definition then of S. So F is the minus, this E operator here is an expectation. So it's minus the expectation of the second derivative matrix, differentiating by vector here, of the log likelihood of our data given the parameters. Okay, so this in here is a familiar object, isn't it? This is the Hessian matrix that we talked about in earlier sections. So in particular, we came across this when we were talking about the Laplace's method for estimating the uncertainty on parameter estimates, or in fact, we used it for approximating the posterior distribution as a Gaussian distribution, if you remember. We had a sort of sketch of a posterior distribution, something like that, and approximated it with a Gaussian, if you recall, something with elliptical contours like that. And that was straightforward enough to do. We simply took the mean of that multivariate Gaussian distribution as our maximum likelihood parameter estimates, and then the clever part was to be able to set the covariance matrix of that multivariate Gaussian distribution to minus the Hessian, the inverse Hessian of the log likelihood. And that made intuitive sense, if you recall, because this Hessian, of course, kind of expresses the curvature of the posterior distribution on our parameters. And if we think just in one dimension for a moment, then when the curvature at the peak is high, it suggests that the standard deviation of the Gaussian approximation is low, so our confidence in the parameter estimates is high. Whereas if we have a sort of very broad posterior distribution like that, the standard deviation is high and confidence is low. So it makes sense that we have this kind of inverse relationship between our Hessian matrix and the covariance of the parameter estimates. And the intuition is very similar here. So the inverse, again, of something which is basically the Hessian of the log likelihood, we're associating with the covariance on our parameter estimates. And so, yeah, the intuition is much the same. But of course, the situation is quite different here, because when we were talking about Laplace's method over here, we had already made a bunch of measurements and made some parameter estimates from them. So we were able to evaluate this likelihood of the measurements given our parameter values. But here, of course, we're in a very different situation where we haven't made any measurements at all. We're thinking about what measurements to make. And so that's why where this expectation operator comes in. We haven't made any measurements, but we can potentially evaluate our expectation of measurements given parameter values and thus the likelihood of those measurements and their second derivative. So that's what we aim to do, compute the expectation of this log likelihood, gives us an estimate of the expected covariance on X. So this is a very general expression here, doesn't make any particular assumption about a noise model, or does assume that we do know a noise model. And for particular choices of a noise model, we can derive some more concrete expressions. So for example, for good old Gaussian noise, we can write down this sort of relatively simple expression for the elements of the Fisher matrix in terms of the derivatives of the model with respect to the parameters. Let's just see where that comes from. So we'll start from the usual place of writing down our likelihood under the assumption of Gaussian noise. Of course, it's our old favorite big product of Gaussian functions. This thing. In fact, I'm going to give each measurement its own sigma. So we're each individual measurement can have its own standard deviation, noise standard deviation. Let's take the logs. So we get log E of A given X. Turns the big product into a big sum, of course. And then we need to differentiate this log likelihood twice, of course. So I'm just going to derive this formula for one particular element of this matrix. So I'm going to differentiate first of all by xi and then by xj. So let's differentiate this with respect to one of the unknown parameters first of all, arbitrarily xi. Oops. So I think there's only really one thing in this expression above that depends on xi, and it is the signal obtained from the model, isn't it? This first term doesn't depend on, let's see, a little k there, doesn't depend on the x's at all. The measurement A doesn't depend on the x's, so it's really just that s thing. So that first term is going to disappear, and we'll just concentrate on the second one. So differentiating that with respect to x then, I think, so we've got a minus sign outside, but the s has also got a minus sign in front of it. So I think those minuses are going to cancel. So I think we're going to end up with 2 ak minus sk over 2 sigma k squared times dsk by dxi. Okay. So let's cancel these 2's, and they cancel each other out. Now let's differentiate again now by a second parameter dxj, so d2 dxi dxj. And now we've got two things that depend on xj, this derivative and the original signal. So I have to kind of use a product rule here to differentiate this expression. But anyway, let's do it. Here's 1 to k So now differentiating the left-hand term of the product first, I think we just end up with, well, it's going to be minus 1 over sigma k squared dsk by dxi, and then times by the other term dsk, sorry, that should be j, shouldn't it? Dsk by dxi. Then differentiating the other half of the product, we're going to end up with plus ak minus sk over sigma k squared, and then it'll be the second derivative of the 2sk by dxi dxj. Okay, so there's our sort of one element of the Hessian matrix, isn't it? The ijth element. Now to get to f, of course, we need to take minus the expectation of this thing. So let's think about the expectation of both of these two terms that we've just computed. Well, this first term is entirely deterministic, isn't it? Because this is just our model. It doesn't have a stochastic element to it at all. It just gives us a number every time we evaluate it at the same point. So I think the expectation of this first term is just exactly that number. So if I write expectation of all that stuff above, then the first term is exactly what we've got there, minus 1 over sigma k squared dsk by dxi dsk by dxj. What happens to the second term? Well, I think kind of know what's going to happen, because you can see the answer down here. So it must, for some reason, the expectation of this must be 0, because we've already got the expression we want on the slide here. Anyone see why the expectation of this term must be 0? I'm going to think about it for a second. In the meantime, so what we've got here then, this is the expectation of this log likelihood, and that of course is minus Fij, which tells us then that Fij is exactly what it says on the slide there. We'll just negate it. Thank you, Sam. Yes, spot on. So the reason that this comes out to 0 is that we did say, of course, that we're going to assume an unbiased estimator, which is so that on average, our measurement should equal its prediction from the model. So it's actually close, Sam. Actually, now I look at it more closely. The thing that's that SK, of course, is deterministic. So its expectation is just itself. The thing that isn't deterministic and is stochastic is the measurement. So its expectation is the value of the model. So of course, then this difference works out to 0. So the expectation of the whole term ends up being 0, just disappears. Okay, so that's where that expression for the Fisher matrix under the assumption of Gaussian noise comes from. So that's great, of course. So, brilliant that the Fisher matrix describes the covariance on our full set of parameters. But of course, what we set out to do was to plug this into some kind of optimizer that we can optimize something with respect to our device settings or independent variables. And to do that, we need a single number rather than a whole matrix of stuff. And so there's a whole range of different scalar valued optimality criteria that we can derive from this Fisher matrix, which can serve as that single number that we need to give as an objective function to an optimization algorithm. Often referred to as the alphabetical optimality criteria. There are loads of them, quite why they're given these different alphabetical titles. I can't quite remember, but there are lots more. So here are just 4 that are quite common ones, but there are loads of them actually. I'll mention a few more a bit later. And they all sort of derive quite simply really from the from the Fisher matrix. So the first one minimizes the trace of the inverse Fisher matrix. Let's just think about the structure of the inverse Fisher matrix for a moment. So of course, it's an estimate of the expected covariance on our parameters. So in general, it's got this sort of structure to it. The diagonal elements will be the expected variances of our individual parameters. Oops. Yeah. And then the off-diagonal elements are the covariances between pairs of those pairs of the parameters. So the top right and bottom left, for example, is the covariance between x1 and xn. And so you can think about that covariance matrix, again, thinking back to Laplace's method as, approximating the distribution on our parameter estimates as a Gaussian, something that has elliptical contours in 2D, ellipsoidal in 3D, and so on. And these variances along the diagonal then kind of correspond to lengths of these contours along the different coordinate axes. Or we could also take eigenvalues of those of that matrix, which would tell us the sort of relative lengths of the major and minor axes of that ellipsoid. So with that in mind, if we think about what these optimality criteria are doing, so A optimality minimizes the trace of the inverse Fisher matrix. So the trace is taking the sum of these diagonal elements, the sum of the variances of the individual parameters, expected variances. So it's kind of summing these lengths of the elliptical contours along the different coordinate axes, isn't it? We're just summing the variances of the individual parameters. So that's what that does. But of course, doesn't really account for these covariances, whereas D optimality minimizes the determinant of the inverse Fisher matrix. So that's sort of proportional to the overall area or volume of these contours. So it does, in addition, account, for the covariances as well as the individual variances. E optimality maximizes the minimum eigenvalue of F. Well, the minimum eigenvalue of F, if F has got eigenvalues, let's say lambda 1, lambda 2, up to lambda n, then the inverse has the opposite, the reciprocal eigenvalues. So if we take the minimum eigenvalue of F, that's going to correspond to the maximum eigenvalue of the inverse of F. So that's the length of the major axis of the ellipsoids corresponding to this covariance matrix. So basically it's trying to squash the direction of largest variance, the variance of the linear combination of all of those parameters that has the largest variance, trying to squash it down as small as possible. So also, kind of makes sense. The last one here is interesting. So T optimality, so maximizes the trace of F. Is maximizing the trace of F the same thing as minimizing the trace of the inverse of F? Well, I don't think so, because it's not true to say that the trace of F is sum of those lambdas, whereas the trace of the inverse of F is the sum of the inverse lambdas, but it's not true to say that those two things, sorry, that's obviously not true, but it's not true to say that the inverse of the trace is the same as the trace of the inverse. So what is this? If we are maximizing this trace, So it's obviously sort of connected to minimizing the trace of the inverse, isn't it? You know, as these get larger, these get smaller. But, you know, there are some sort of pathological examples, aren't there? For example, if, say, lambda 1 up to lambda n minus 1 are all massive compared to lambda n, then, you know, these terms are going to dominate the maximization of the trace of f, whereas the inverse of this one is going to dominate the minimization of the trace of the inverse of f. So, you know, the two can end up doing quite different things, and maximizing the trace of f, you know, really isn't what we want to be doing. You know, it doesn't correspond with what we set out to do in the first place, which was to minimize these, you know, these variances of our different parameters. So it's not quite, you know, not the most satisfying choice of optimality criteria in this one, but anyone spot why it's a not necessarily the right thing to do, but it's a useful thing to do, and actually somewhat more practical to do than these other ones in some scenarios. Anyone see why? Any thoughts? Suppose, you know, we're working on a problem where there's a large number of parameters, you know, 100, say. How big is f if there are 100 parameters? Well, it can be 100 by 100, isn't it? Yeah, thank you. So Sam points out that for T optimality, we don't need to invert the matrix F, which is, you know, if F is large and we've got a number of parameters, that can be a very significant computational advantage. For all of these other things, we need to effectively compute the inverse of F, but we don't for this. So it can be much more, the optimization loop can be much more rapid. And although it can be sort of vulnerable to situations like this one, where you maybe have kind of large differences between the eigenvalues of f vary over a very wide range, then it can do slightly weird things. But if that's not the case, and all of the eigenvalues are reasonably similar, and so this kind of these contours are approximately spherical, then actually you get a pretty good correlation between the inverse of the trace of f and trace of the inverse of f. So it can actually, in practice, often work very nicely, but much more quickly. Okay, let's think about some actual concrete models. So let's start with linear models and our simple linear least squares problem. So under that, in that situation, we end up with a very nice simple expression for f, which is basically just the square of our design matrix, appropriately normalized by the right noise variance. So this would be when we can assume that the noise variance is the same on all the measurements. But even when we can't, we still get a pretty nice simple expression for f in terms of the design matrix for the linear problem G, and this W, which will also be familiar from when we were talking about weighted linear least squares, is just a diagonal matrix with the inverse variances of the individual measurements along its diagonal. Let's see where this expression comes from. Pretty straightforward from the expression that we derived up here, which actually I'm going to copy because I want it. And let's start with writing down a linear model. So of course we can write those as S if it's linear. So it's just a linear combination of, let's say, Gi and Xi. I is 1 to n. And then if we to plug that into our equation for the elements of the Fisher matrix under the assumption of Gaussian noise, which is, if you'll recall, the assumption of the linear least squares problem, we can then derive expressions for the elements of the Fisher matrix very easily, because of course ds k by dxi would simply be g ki, and so plugging that into the expression for fij here, we end up with simply okay, and if we then assume that the noise standard deviation is the same on all the measurements, then we can just take that sigma out of the sum. And that's simply the dot product of the ith and jth columns of the design matrix, and so hopefully you can see how that expression for a single element turns into this expression for the whole matrix. Let's sort of think about that in a particular for a particular simple model. Let's go back to one of our old favorites, a simple linear model, one that we used for the child's heights all those times. So we're fitting the model H is my plus c, and so writing out our matrix equation, our list of measurements is then just the h's, hy up to hk. Our list of unknowns, of course, the two unknown parameters of the linear model m and c, and that of course gives us this design matrix, which we've seen several times, where we have a column of the years at which we made the measurements, those multiply the m's, and then a column of ones to multiply the c. So we get that sort of simple design matrix. So plugging that then into our formula up here for the Fisher matrix gives us something quite simple. It's because these sort of dot products of the columns of G, isn't it? So F would be then the top left element of F is going to be the sum of yk squared. Dot product to the first column of itself. Then element 1, 2 here would be the dot product of column 1 and column 2. So that's simply sum of the y's. Same thing on the bottom left. And on the bottom right, we just simply get the sum of 1 dot product of this column of 1s with itself. So get that quite nice, simple form for the Fisher matrix for that problem. Let's see if we can see if that, this corresponds with our intuition about where to put points for a simple linear model. We've thought about this before, of course, but let's suppose we start with a very simple 2-point design. Let's say Xi then, our design, it just has we're just going to make 2 measurements. We'll fix one of them at y is 1, and we'll allow the other one to vary to some point capital Y. And the question is, where do we want to put the second, where do we choose the second point capital Y? I think we know the intuition behind this because we've talked about it before, but just to remind you, so the problem is we make one measurement at y is 1 here, and then we get to choose another point somewhere at big Y, and we're assuming that the standard deviation on each of these measurements is independent of of where it's made. So they've all got the same standard deviation. We saw this before, of course, and the intuition that we came up with before is because, the further we put these two points apart, the smaller the range of possible lines that can kind of fit within similar error bars on those 2 points. So I think our intuition here is that big Y should be as far along that axis as we can possibly put it. But let's see if the Fisher matrix tells us the same thing. So substituting this design then into this design psi into this Fisher matrix, I think we end up with F is then, okay, so top left sum of the Y squared is going to be 1 plus big Y squared. Then I think on the off diagonal terms, we just get 1 plus Y. And the bottom right term, sum of ones, well, there's only 2 measurements, so it's just 2. Okay. So there's our Fisher matrix for that specific design. Let's pick one of these criteria then. So I suggest we go with this D optimality. We'll compute the determinant of F here. I'm sorry, of the inverse of F. Of course, the determinant of the inverse of F is equal to the inverse determinant of F. It is true to say, unlike the trace, it is true that inverting the determinant of F gives me the determinant of F inverse. So I'm just going to work with F. So the determinant of this F then is product of diagonal elements minus product of off-diagonal elements. Actually, I've missed off a sigma, haven't I? Should, of course, have 1 over sigma squared here, strictly. Just put it back in for completeness. And that's going to give me a 1 over sigma to the 4 multiple of that for this, not that it really matters. Okay, so let's expand that out. What does it give me? Sigma inverse square of variance times by 2 plus 2y squared minus 1 minus 2y minus y squared equals, you can see what's going to happen, y squared minus 2y plus 1. Okay, so it gives us that for the determinant of F. Now, according to D optimality, we want to minimize the determinant of inverse of F. So that's equivalent to maximizing the determinant of F. Well, how do we maximize this determinant of F? Well, we take Y as massive as possible. Okay, so that, I think, corresponds to our intuition about that problem. Let's just adjust that problem slightly. And so rather than assuming that the standard deviation of the measurements is the same for all of them, how about we assume instead that the standard deviation of the measurements increases with Y. So let's suppose that let's say the variance is proportional to Y, so equals some constant alpha times Y. So that makes things a bit more interesting, because so now as we from our single fixed point 1, so that might have a certain variance to it, but as we increase Y from there, the variance increases linearly with the value of Y. So question is, does it still make sense under those conditions to take our second point for estimating the parameters of a line model as far away as possible? Because the further we go away, the more noisy that measurement gets. And so, joining up the tops and bottoms of the error bars again, it's not obvious at all that we want to go infinitely far away to pick the best second sampling point. we have the tools now, of course, to answer this question. So let's plug this into our Fisher matrix and see what happens. So now then, okay, let me paste it again here just to remind ourselves of the formula. Here it is. So I can then write now F11 would be, okay, so it's going to be sum of K1 to K, 1 over sigma K squared. So this term here, of course, is G K I, GK1, sorry, we're looking at element number 1, aren't we? And the next one is also GK1. Okay, so we know that that equals YK. So the GKs are going to give us YK squared, whereas this standard deviation is, we're writing as alpha Y. So that, I think, comes out as the sum from K1 to K of, well, it's going to be, so we've got Y on the bottom and Y squared on the top. So I think we end up with YK over alpha. Okay, let's do the same thing for F12. So that then, of course, same thing, 1 over, we know our sigma squared K is, of course, alpha YK, but now we're going to have GK1 times GK2. So GK1, of course, is YK, but GK2 is just 1. So I think for F12, we end up with sum of just 1 over alpha. And lastly, F22, now we have, again, sum over K, 1 over our sigma K squareds, which are alpha YK, and then it would be GK2, both of which are 1, of course, 1 times 1. So we end up with sum K, 1 over alpha YK. So that gives us, plugging that into our full matrix F, we've now got, well, what was F11? Sum of YK over alpha. YK over alpha. The off-diagonal terms were both sum of 1 over alpha. And the second diagonal term, 1 over alpha YK. Okay, interesting. Let's substitute in our 2-point design. That gives us, F is then, okay, so we've got 1 over alpha plus big Y over alpha. The off diagonals are just 2 over alpha, aren't they? 2 over alpha. And then we've got 1 over alpha plus 1 over alpha big Y. Okay. Let's take, I think we could take a factor, we're going to compute the determinant of this. I think we can take out a factor of alpha to the -2, can't we? And then multiply, so we're going to have 1 plus y times 1 plus y to the -1 minus 4 from the off-diagonal elements. It's all multiplied by alpha to the -2. Okay, and multiplying that out, I think what do we get from this first term? We're going to get 2 plus y minus 1, aren't we? So I think we end up with y plus y minus 1 minus 2. Alpha minus 2, y plus y minus 1 minus 2. Okay. So once again, I think, even despite this, the standard deviation or the variance increasing linearly with y, we still find that according to the Fisher matrix, we want to take our second operating point, y, as far away as possible. You know, the bigger y is here, the bigger the determinant of f. And so we maximize determinant of f, minimize the determinant of inverse of f. Let's just do one more of these for good measure. All right, so that time we had the variance scaling linearly with y. What happens if instead we make the variance scale quadratically with y? So let's say that the variance is now equal to alpha y squared. So every time, yeah, quadratically increasing variance as we move that position further and further away. So it's getting, you know, the noise increases very, very rapidly, quadratically, as we move that point further away. Let's do the same thing and see what happens. So F11 then I think becomes, well, it's going to be sum over k 1 over, so now we're going to have alpha yk squared for our sigma k squared term. G1k, of course, is yk, and we'll have the square of that for position 1, 1. So I think then for position 1, 1, we end up with just sum of 1 over alpha. Those yks all cancel each other. Similarly, for F12, so we're going to have, again, 1 over alpha yk squared, and now we'll have yk for G1, but just 1 for G2. And so that will give us, I think, sum over 1 over alpha yk. And for F22, see what's going to happen. 1 over alpha yk squared times just 2 ones this time, isn't it, from the G2, the G2 elements. So that will give us sum over 1 over alpha yk squared. Okay, let's construct f again. It is. So it looks like that. Let's substitute our 2-point design again. And we end up with uh, 2 over alpha there. So these off-diagonal elements are going to be 1 over alpha plus 1 over alpha y. 1 over alpha. And then here we have 1 over alpha plus 1 over alpha y squared. Okay. Let's take the determinant. So I can take the alpha out again. And we end up with what? 2 times 1 plus y to the minus 2 minus 1 plus y to the minus 1 squared. Okay, let's multiply that out and have a look at it. So I think we've got 2 plus 2y to the minus 2 minus 1 minus 2y minus 1 minus y to the minus 2. Let's group some similar terms. I think we end up with y to the minus 2 minus 2y to the minus 1 plus 1. In other words, 1 minus y to the minus 1 squared. Interesting again, because what does that mean? Well, as y gets bigger and bigger, of course, this 10, so it reaches an asymptote, doesn't it, of alpha to the minus 2. But it approaches that asymptote again as y gets bigger and bigger. So even under those circumstances, where the noise is increasing quadratically as a function of the position of that sample point, even then, we still want to push that point as far away as we possibly can. So yeah, you have to really add some quite dramatic noise to get away from that intuition at the second point for estimating a linear system be pushed as far away as possible. In fact, if you increase that power any higher than 2, it starts to reach a maximum point at some point, some finite point. Okay, anyway, that was just a sort of point of interest. Don't worry too much about that if you got a bit lost in the middle of those calculations. Where were we? Okay, so I was thinking about some linear models and really just sort of showing that the optimal sampling points that we can derive from this matrix F match our intuition, and you can do some quite nice things, figuring out where to put those operating points, even in scenarios where it's not obvious at all where that second point should go. Let's move on and think about some non-linear models. First of all, let's just revisit an old friend here. So the Ball matrix Ball model from diffusion MRI. So this fella here. So a non-linear model, of course, but as we've seen from early stages of this series, we can linearize it by taking the logs of both sides. Let's do that. So if we can write as usual, log of SB into log of S0 minus BD, because I want to think about the design of this experiment for estimating the diffusivity. So if we linearize and treat it as a linear least squares problem, of course, it ends up almost identical to what we just looked at, doesn't it? I can write my vector of pseudo vector of measurements log SB1 up to log SBK, and then equal to my list of unknowns. That's D and S0. I'm just going to use subscript for shorthand, and that gives me, again, the old sort of familiar design matrix G, where the first column is a list of B values minus B1 up to BK, and the second column is a list of ones. That, of course, gives us the Fisher matrix, very similar to what we just looked at for the other linear problem. So we get something like sum of B squareds for element F11, sum of minus B's for the off-diagonal elements, and sum of ones for the second diagonal element. Now, let's suppose we're just trying to figure out a single non-zero B value for our very simple experiment of just estimating the diffusivity. So that's equivalent, again, very similar to what we just thought about. We define a 2-point design psi, which is now, the first point would be 0, B value of 0, and a B value of something, B. These should all be BKs, shouldn't they? 1 over sigma squared, of course. We'll assume same noise standard deviation on all the measurements. So anyway, let's substitute in this design again. So F is then sigma squared, and we're just going to get B squared B 2. Determinant of F, you know what it's going to tell us. Just gives us 2B squared minus B squared, isn't it? So it's sigma minus 4B squared. So it tells us, again, to maximize the determinant of F, we take that the non-zero B value as far away as high as we possibly can. But yeah, that doesn't feel quite right, because if you think about it, how does our signal behave? As a function of B, the signal, for some sort of moderate diffusivity, say, well, it's exponential, isn't it? So it sort of gradually reduces to zero like that as B gets higher and higher. And what differentiates the diffusivity, the parameter that we're interested in, is that it decays at different rates for different diffusivities. So if we have a lower diffusivity than the one causing this black curve, then it would decay more slowly, but still eventually reach zero, same as the other one. If we have a higher diffusivity, it would decay more quickly and reach zero a bit more quickly. But it's pretty clear from looking at these curves that if we want to distinguish between diffusivities or make the best estimate of a diffusivity parameter, making measurements way up here at the highest p-value possible, where all of the signals disappeared and whatever the diffusivity is, the signal is zero, cannot possibly be the best experiment design. Surely we're better off making measurements at some p-value around here, where we've got contrast between the measurements for different p-values. So what's going on? Why is this mechanism telling us something that is clearly untrue, that we should be measuring at a very high p-value, when clearly a moderate p-value gives us better estimates of the parameters? That's a question for you guys. What's happening? Something's gone wrong. I think the answer is clear, isn't it? It's going to be, as we saw before in some other scenarios, this step, this linearization step, is causing us some problems. Yes, thank you, John. The noise assumption only held true before taking the logs, exactly. So, even if we could assume Gaussian noise on the original signals, we can't assume that after we take logs, and that throws everything off, because that expression that we used for the Fisher matrix relied on the assumption of Gaussian noise. Let's think instead then about this problem properly and treat this model as a nonlinear model, which it properly is, and there we can more reasonably make an assumption of Gaussian noise. Okay, so our model then, let me just write it again. SB is S0 e to the minus BD. So of course we're going to need derivatives of this model to compute these elements of the Fisher matrix here. I need derivatives of that model with respect to each of the unknown parameters. That's S0 and D. So let's write those out. So ds by ds0 is then simply e to the minus bd, and ds by dd is what? Minus S0b e to the minus bd. Okay, so given those, I think we can construct a Fisher matrix. Let's write it here. So F is then, so let's put together element 1, 1 first. So that's where where both I and J correspond to S0. So I think there we'd end up with 1 over sigma squared out here. E to the minus 2b, sorry, I've got to sum it, sum over k of e to the minus 2bkd. And then, so in the off-diagonal elements will be the product of these two derivatives. So that will give us k minus S0 bk e to the minus 2 bkd. Same thing down here. And then the last one is the square of this derivative with respect to d. Okay, so there's the Fisher matrix that we get for this. What do you immediately notice about this, the Fisher matrix, compared to the Fisher matrices that we got for these linear systems, like this one, for example, or some of the earlier ones that we had? There's a key difference. There was another one, all of them, in fact, even the general expression, where was it? Going right back up here somewhere. What was it? Oh, done too many calculations. This one, sort of general expression for the Fisher matrix for a linear system. There's a key difference. If I flip back down again. Yeah, thank you, Sam. So the point is that this Fisher matrix contains the unknown parameters, D and S0. Whereas if you look back to the Fisher matrix for the linear ones, it was completely independent of all the unknown parameters, depend only on G, which itself depends only on the device settings and not the unknown parameters. And that's a beautiful thing for linear least squares problems, because it means that whatever optimal design we derive is, holds true, whatever the values of the parameters. Whatever the slope and intercept of a linear model, it's always true to say that we want to put those two sample points as far away as possible. We can't make that kind of statement for a nonlinear model, because now we can see that the Fisher matrix, and therefore the optimal design, depends on the model parameters themselves. So it puts us in this slightly circular position of having to, in order to define the Fisher matrix and define an optimal design, we need to specify values of the individual parameters. But of course, the whole reason that we're making measurements and doing the experiment is that we don't know the values of those parameters. So we end up in a slightly awkward position. We'll come back to that in a second. Let's just work through this example of estimating the diffusivity here, first of all, and go back to our 2-point design. So psi, we're going to measure 2 points, one at b value of 0, one at a b value of b. And let's substitute that into this Fisher matrix, see what it gives us. So F is then, inverse sigma squared. So what do we get? We're going to have this top left term. So when b is 0, that's going to give me 1. When it's not, it gives me e to the minus 2bd. All of the other ones, the first terms in those sum become 0, don't they? Because the b value is 0. And so I think for the top right, we're going to end up with minus S0 b e to the minus 2bd. Same on the bottom left. And bottom right will be S0 squared b squared e to the minus 2bd. Okay, let's work out our determinant again. So multiplying these diagonal terms then, I think we end up with S0 squared b squared e to the minus 2bd plus S0 squared b squared e to the minus 4bd. And then the off diagonals will give me so minus S0 squared b squared e to the minus 4bd again. So I think these two are the same, aren't they? They cancel each other, which is nice. So we end up with just that single term there. And so if I'm looking for a maximum point in this determinant of f, at that maximum point, the derivative of that determinant with respect to the thing I'm trying to optimize, which is b, must be 0. So let's differentiate this with respect to b. I think we end up with sigma minus 4 S0 squared 2b e to the minus 2bd plus b squared minus 2d e to the minus 2bd. That, of course, equals 0. So lots of things kind of conveniently quite cancel. If we set this equal to 0, we can get rid of these sigmas, we can get rid of the s squareds, we can get rid of one of the b's, we can get rid of these 2's, we can get rid of the e to the minus 2bd's. And actually all we're left with then is, so this term has just become 1, the first one, and the second term has become minus bd. So all actually comes out quite simply, and we end up with, at that maximum point, b is equal to 1 over d. Very simple. So it suggests that we take the b value to be simply 1 over the expected diffusivity. And actually, if you think about it, so the diffusivity that we expect in brain tissue is at body temperatures, something like 10 to the minus 3 millimeters squared per second, which would suggest, if we take 1 over that, that we should be setting the b value, if we're imaging a live human brain, to 1,000 seconds per millimeter squared. Coincidentally, or not coincidentally at all, as it turns out, precisely the b value that is used in the data set that you've been looking at in the coursework. And actually that's exactly where this comes from. It's, you know, the choice of b value in that kind of experiment comes from exactly this kind of calculation. Okay, probably enough calculations. Let's see. So yeah, key thing about nonlinear estimation then is that the Fisher matrix now depends on X. And so in order to construct that Fisher matrix and an objective function for optimizing the experiment design, we now have to make a choice about what parameter values we want to optimize for. So various ways of doing that. You can just pick a single representative value, as I kind of did here. But often, you know, people in, you know, interesting experiments can also usually result in various different values of those parameters. So you might want to pick a representative set of X and then average the Fisher matrix over that representative set and optimize for that kind of average Fisher matrix. A couple of further practical considerations. So one thing is that we have to think carefully about the scale and units of the different parameters. Let's think, you know, sticking on this diffusion model here, the structure of, you know, F inverse, as we saw earlier, has, you know, the structure of a covariance matrix. So for this particular model, where our two unknowns are S0 and D, it sort of looks like, you know, variance of D and variance of sigma squared, sorry, variance of S0 on the diagonal, and then the covariance is the on the off diagonal, the covariance of the two parameters, something like that. But if you think about, you know, the scale of these variances on the diagonal, so, you know, D, as we say, approximately 10 to the minus 3, and its variance, you know, if its standard deviation, say, is approximately the same order, then, you know, we might expect the variance of the D to be, you know, it could be anything down to, you know, 10 to the minus 6, something like that, quite a small number. Whereas S0, you know, typically gets set, you know, to something in the integer range on a computer. I think in the data set that we've got, it's something that's around about 1,000, isn't it? 10 to the 3. And so its variance, you know, let's say something like the square of that up to 10 to the 6. So, you know, a lot of orders of magnitude between these two. Sorry, these are supposed to be variances rather than standard deviations. A lot of orders of magnitude between these two numbers. And if we try to, you know, if we look back at our optimality criterion here, let's say we sort of minimize the trace of f minus 1, that would mean sort of, you know, minimizing the sum of these two values. That objective function is going to be entirely dominated by this one, which is 12 orders of magnitude bigger than the other. It doesn't, that it's not going to care anything about small variations in this. It's going to focus entirely on minimizing the variance of S0, which is actually not really the interesting parameter at all. The one we're interested in is D. So you have to be a bit careful to avoid that kind of problem, to make sure that the scale or the units of these two things, choose units of these two things so that the variances come out around about the same scale. And very common thing to do, which was on that slide I just left, is to normalize by this outer product of the choices of parameter values. So that is, so XX transpose would be whatever values of XX transpose is D and S0 outer producted with itself, DS0, which gives the matrix D squared, DS0, DS0, S0 squared. So if you normalize F by that matrix, just element by element, then it brings everything into the right kind of scale. Prior choice for parameter settings. So I just talked about this briefly, didn't I, on the previous slide? Oops, gone too far back. So, we could, for nonlinear models, of course, we have to choose values of X. So we could just choose a representative set, sort of tempting to be a bit Bayesian about it and say, maybe we should work out this, something like F tilde, which is kind of the integral over all possible x's of f of x, multiplied by some occurrence probability of each combination of parameter values. Actually not such a great idea in practice if you think about it, because it's not necessarily true. So this would weight the sort of average Fisher matrix very strongly by what the most common combinations of parameter values that we observe are. But those most common ones are not necessarily the most interesting. If you imagine yourself sitting in front of a large hadron collider waiting for a Higgs boson to appear, one in every, whatever it is, 10 billion experiments actually produces the interesting output. But if we've optimized our experiment design weighted by what most commonly appears, it wouldn't consider that interesting outcome at all. It would focus entirely on the more mundane output that happens, 999 million times out of a billion, and not optimized for the interesting case at all. So actually better to do what I said on the previous slide, which is just to pick a small number of individual interesting representative combinations and average over those. Final practical consideration is that these optimizations can be hard. If you're even thinking about our simple diffusion model, if we were to really do that properly, we didn't just make 2 measurements, did we? We actually make, that data set that we've been using uses 108, and to optimize the choice of just the B values among those 108, it requires solving a 108 dimensional problem, searching in a 108 dimensional space for a single point. Not easy, and that's even before you start thinking about the directions of the different the gradient directions for each of those measurements. So often these things can really require the heavy artillery of optimization to find good solutions. Okay. Any questions so far? I'm going to go through an example in a second, just a quick run through of an example. Okay, question from Sam. For the earlier examples of linear models with linearly and quadratically growing noise, can't we alternatively maximize the determinant of f with y tending to 0, as both examples contain a inverse y term rather than making y as large as possible? I think so. I'd have to think that through, but so I think, let's flip back to it. Yeah, so I think that's true, isn't it? There's an alternative solution which sets Y to be 0, because at that point there's 0 error on the value, on the measurement, according to our simple model. So I agree, that would be an alternative solution, yes. Good point, thank you. Anything else? Okay, let me run through this example. We'll probably still have 5-10 minutes at the end anyway, if you think of anything else. Example 1, it's actually the only example in the slides. There's another example in the notes if you want to look up there. So we're going to think about a different modality that we haven't considered before, which is dynamic contrast enhanced computed tomography. So computed tomography, or CT, is an X-ray, uses X-ray, and basically takes an X-ray image in lots of different directions so that you can then recompute a 3D picture of the inside of an object. Dynamic contrast enhanced CT takes multiple CT images over a period of time after injecting a subject with a radio tracer. And what that tracer does is to enhance the CT signal. So wherever it appears in the body, you see increased brightness in the image. So that's interesting, but what the really interesting thing is how that brightness varies over time, because it tells us how quickly each piece of the body, each sort of different bit of the body, absorbs that radio tracer and then manages to kind of to wash it out again. And one of the key applications of that is looking at cancer tumors, because that absorption and washing out of the radio tracer tends to happen more quickly in aggressive cancer tumors than it does in more benign cancer tumors. Let's just, before we get into the details of that, let's think about why that might be. So here is a nasty looking cancer tumor. So tumors, when they grow, they tend to hijack the body's vascular system. So they create their own blood supply by linking into the body's blood supply. So here's an artery coming in, and this tumor has grabbed some branches off this artery and turned them into its own blood supply, allowing it to, providing it with nutrients and allowing it to grow and so on. And there'll be a similar kind of venous system, taking deoxygenated blood away from the tumor. Something like that. Now, the more quickly a tumor grows, i.e. the more aggressive it is, the less good quality those blood vessels tend to be, because it creates them very, very rapidly and in a sort of kind of slapdash fashion. And so what happens to the blood vessels as they're created very quickly is that the walls of them tend to be not as well built as blood vessels in healthy tissue, and they become leaky. So I'm just indicating that here by sort of adding some holes to them, like so. And that means that when some radio tracer arrives at the tumor, so a radio tracer gets injected, enters into the blood supply, comes down the arteries and will come into a tumor. And because the blood vessels in the tumor are leaky, they're highly permeable, the radio tracer will very rapidly find its way out into the body of the tissue of the tumor. And similarly, very rapidly, find its way back in to the veins in the tumor and get washed out quite quickly through the sort of proximal veins and sort of eventually find its way back to the liver and get sort of get excreted. But the point is, the more permeable the blood vessels in the tumor, the more quickly we see uptake of the radio tracer and washout of the radio tracer. And so overall, we tend to see that increase in concentration of the radio tracer over time causes a change in the intensity of the image that looks something like this, this curve here. So it will increase as it gets absorbed and then decrease as it gets washed out. And for a particularly aggressive tumor, that increase happens very quickly like that, and the washout happens quickly. For a less aggressive tumor, it might look like that black line, and for more healthy tissue, it might, execute an even slower trajectory, a bit like that. So the key parameter that we'd like to estimate from these kinds of curves of intensity that I'm showing on the bottom there is the permeability of these blood vessels, because that informs us very directly about the aggressiveness of a particular tumor, and that can inform our treatment strategy. So that's what contrast enhanced CT is used for. Here's I'm not going to pick through the details of the maths here. You can, it's in the notes if you want to have a closer look at it. But here is a signal model that links these intensities in this curve and how they change over time to interesting parameters of the model, including the key one, which is this PS quantity here, which is the permeability. Very briefly, what this is showing, all these, the C1 and C2 here, are the concentrations of the radio tracer in the blood supply of the tumor and the body of the tumor. C2 is the body of the tumor, C1 is the blood supply of the tumor. So the rate of change of that concentration in the blood supply of the tumor is proportional to the blood flow rate, that's this thing phi. Ca, this is the arrival concentration in the sort of feeding artery, the difference between that and the concentration that's already in the blood of the tumor. And then the permeability times the difference in concentration in the blood and in the tissue. And then similarly, concentration in the tissue is just proportional to the permeability times the difference in concentration between the blood and the tissue. So intuitively, the bigger the difference in concentration, the more quickly it leaks out, and the higher the permeability, the more quickly it leaks out. So you can solve this sort of coupled pair of differential equations to give this what we call an impulse response curve. So that's a curve that has this kind of shape, but the shape that you would get if the injection sort of injected all of the radio tracer all in one instant, whereas of course it doesn't. The injection takes 10, 20 seconds or so. So you have to convolve that with the sort of arrival function of the time of the profile of injecting the tracer into the bloodstream. Anyway, eventually it gives you this expression for the trajectory of the intensity over time as a function of various important parameters. The key one being the permeability. These are some volume fraction parameters and a blood flow as well. Okay, so non-trivial, highly nonlinear model. So the question is then, what's the best experiment design to estimate the key parameters, in particular this permeability parameter? And so one sort of strategy might be that we just make measurements. By the way, each measurement is a whole image of the, whichever bit of the body we're looking at. So we're getting, as with the diffusion imaging, we get an intensity in each pixel. But it takes about 10 seconds to acquire one image, one CT image. So we could just acquire images, every 10 seconds, very densely for the whole, possible span of these intensity trajectories. And it probably takes about 10, 15 or maybe 15 or 20 minutes before the signal returns to the normal level. So, if we can take a measurement every 10 seconds, that would mean, something like, I don't know, 120 or even 200 measurements over that time. Why would we not want to just acquire as many measurements as we can, do you think? Why not do that? I mean, the more measurements that we get, the more information we can. We've got a lower limit. We've got an upper bound placed by the fact that we can only acquire one measurement every 10 seconds. So why not just max that out and get as many measurements as we can? Anyone know? Well, not sure if anyone's typing or not, but I'll tell you the answer. X-ray isn't good for you, of course. You know, every time you acquire one of these images, you give the patient a radiation dose. And that's not a good thing to give people. You know, you want to keep that radiation dose to the minimum possible. So there's a kind of standard NHS CT dynamic contrast enhanced CT protocol, which requires 70 images spread over the 15-20 minutes that that the exam goes on for. And the question in experiment design then is, where should we put those? What time points should we place those 70 measurements that we have available? So I forgot to say, actually, I'm reporting some results from this paper back in 2010 by Prevost and colleagues that looks into this problem. So they set up an experiment design objective function. I'll ask you, so can anyone recognize what optimality criterion we're using here? Have a flip back and have a look. F here is the Fisher matrix. P here is the set of parameters. So this is what we were calling X previously. They called it P. So here, the purpose of this P to the -2 is simply the same as by normalizing by X-ax transpose here. So getting the scale right. But basically this is just a function of an appropriately normalized Fisher matrix. What's it doing? It's summing over the 4 parameters the ith element of the inverse Fisher matrix. Thank you, A optimality, I think that's right. It's the one where we're looking at the trace. Yeah, minimizing the trace of the inverse of F, exactly. Let's go back there. Okay, so yeah, we set up an optimization where we're using A optimality and minimize the trace of the inverse Fisher matrix. They pick a particular combination of these parameters. It's a combination that's sort of typical for a malignant tumor, and then use this. This is a self-organizing migratory algorithm that they use to optimize the positions of those 70 points, subject to the constraint that they're at least 10 seconds between each pair, and for just this single combination of parameters. Even so, this is still a 70-dimensional optimization problem, not easy. This is what comes back from their first go at that 70-dimensional optimization problem. So here's the kind of timeline in seconds, and it places the time at which we acquire these 70 measurements at these pink circles at the bottom here. So what sort of, do we see any structure appearing in this solution? Anyone spot some structure there? The pink circles up here are just projecting it back onto the intensity trajectory that corresponds to that malignant tumor setting that they use to optimize the experiment design. So, well, I think, there is a bit of structure here, isn't there? It looks like there are sort of the clusters of measurements around potential locations of the peaks. So something like that's going on, isn't it? It looks like there are groups of these measurements clustering around interesting points on this curve. So strangely enough, it doesn't seem to focus exactly on the peak, but sort of, groups nearby, which presumably actually do inform on where the peak is, and then maybe these kind of inflection points down here, are informative of some of the other parameters. But then there's also this. So all right, there are 4 little clusters like that, but then there also seems to be a sort of scattered group here as well. And so, whether those are important in the estimation of the parameters, or whether they're just a product of, the optimization of this 70-dimensional problem not really converging, is quite difficult to say. We probably don't find the global minimum of a 70-dimensional objective function. But the hope is that we get reasonably close. So hard to say, if those other points are important. But what they did next is interesting. So having done that initial experiment to get kind of a feel for what the optimal design might look like, they then explored various parameterizations of that design. So they started with a very simple one. So here is a simple way of defining a protocol. And in fact, this is the NHS kind of a dynamic contrast enhanced CT protocol. You start by having a bunch of measurements as densely packed as possible, so all the minimum of 10 seconds apart. And then after a while, you move to a much bigger interval between measurements for the remainder of the exam. So you can think about that protocol as having two parameters. One is the balance of measurements in the dense sampling bit compared to the sparse sampling bit. Must add up to 70, of course, so that's just one parameter. And then there's the spacing of the sparse sampling bit. That's parameter number 2. There was another similar suggestion from a previous piece of work that said, well, actually, rather than having these equally spaced, how about we just sort of, make them more and more sparse as the time goes on. So we'll keep the very dense sampling at the start and then have spaced out ones that increase their spacing gradually over time. And this protocol has 3 parameters. Again, the ratio of dense sample points to sparse sample points. And then there's the initial spacing, that's the second one. And then the rate with which the spacing increases, that's the third one. Then there's the full freedom, 70-dimensional optimization. But what Prevost and co then did was try to parameterize what they thought this looked like. So they then said, okay, well, we can construct, I think it was a sort of 9 or 10 parameter model where there are 5 groups of measurements, cluster 1, cluster 2, cluster 3, cluster 4, and then the sort of sparsely sampled group number 5. So first of all, there are 4 parameters that define the relative numbers of points in each of those 5 groups. And then there's so that's 4 parameters. There's the starting positions of each of them. That's another 5 parameters, so that's 9 already. And then there's the spacing of the sparse group. So I think there are 10 parameters in total. And then optimize the parameters of that rather than the full 70-dimensional problem here. They reduce it to a 10-dimensional problem, which is much easier to solve. And interestingly, if you look at the values of the best values of the objective function, this A optimality function, for those 4 parameterizations, that last one produces the lowest value, which is interesting in itself because actually, strictly, this 70-dimensional one should always do the best, shouldn't it? Because it's the most flexible. It should be able to achieve anything that this last one can achieve. But and so why does it? Why doesn't it produce as low a value of the objective function as this one? Anyone hazard a guess as to why it doesn't seem to do so well? I mean, it certainly has the flexibility. It should do at least as well in terms of objective function. Problem, of course, is that the search is extremely hard. Yeah, I think it probably not so much converged on a local minimum, just hasn't converged at all because that search is so hard. It may have found a local minimum, but it certainly hasn't found the global minimum solution, whereas it's easier to find or at least get closer to the global minimum when there's only 10 dimensions to search over rather than 70. Anyway, the sort of final outcome then of this paper was pretty interesting, really, because comparing to the NHS scan, so they ended up having designed various sort of optimal protocols like this. They then compared using Bootstrap actually to evaluate the precision with which you can estimate this permeability parameter. So using the NHS protocol that came out at around about 20% precision, the variance of 20% compared to the actual 20% of the actual value. Whereas using the optimized protocol, you can reduce that variance to about half. But perhaps even more interesting is that if you use a similar optimization for smaller numbers of sampling points, you can actually reduce that number of sample points down to half, down to 35 points rather than 70, and still get more precise estimates of that critical parameter, which is pretty interesting. Saving half the dose of half the radiation dose for each patient, and yeah, so just shows you the kind of power of designing the experiment properly. Okay, just a couple of last sort of variations on the problem and summary to wrap up. So we've concentrated on quite a simple scenario really, where we have a number of measurements to make, and we're just going to choose them all a priori and then go on and make those measurements in some application. But one variation is to do adaptive or sequential design, because one of the problems that we encountered was that we had to make a choice about what the expected parameter values were before we started. But that, of course, is the whole point of the experiment, is to estimate those parameters. But the idea in adaptive design is that you start by making some of the measurements you've got budget for, and that gives you at least a handle on what the parameter values might be, that you can then feed into an optimization to choose the remaining, to choose how to spend the rest of your budget within that simple experiment. So the way I've written it here, you might make the first K measurements and use those to inform, what's the most informative next measurement I might make. But you could go further on that and start with the first K/2 measurements and use those to optimize the last ones. Of course, the issue there is that if you're under time pressure, such as got a patient in an MRI scanner, then you often don't really have time to perform a 30-dimensional optimization to choose the last few measurements while they're lying in there twiddling their thumbs. But in some situations, that can you can do that sort of thing. We've concentrated on design for estimation, i.e., we've set up our optimization to optimize the experiment design to maximize our confidence in parameter estimates. That's not always the goal. Sometimes it might be that we want to optimize the design to provide the best predictions of future measurements that we can. And the optimality criteria are different for that scenario than they are for optimizing the precision of parameter estimates. And there's a whole other set of optimality criteria that are designed specifically for that purpose of maximizing accuracy of future measurements. And similarly, you might want to set up a design to choose between different models. And again, there's a bunch of optimality criteria which are designed to maximize the discrimination between different models. Okay, so that's all I'm going to say. Just to summarize, so we've talked about optimizing experiment design for parameter estimation, sort of use the Fisher information matrix as a key tool in doing that, and use that to derive various optimality criteria that we can optimize. So just to think a bit about, what are the scenarios under which we need to do that? So, one time that, this kind of experiment design is an absolute necessity is if you're asking a question like, is it possible to estimate parameter X using this kind of measurement? So actually the other example in the notes is about using diffusion imaging to estimate the diameter of axon fibers. I mentioned this a little bit yesterday. So you can get, at least in theory, you can get some sensitivity to the diameter of axon fibers from diffusion MRI measurements. But about 10 years ago, there was less than that, actually, probably 5 years ago, there was a flurry of papers exploring the question, can we, with human MRI scanners, get sufficient sensitivity to the axon diameter to be able to measure it and map it over the brain? And of course, you can't answer that question if you just take a random, or some sort of ad hoc combination of measurements and try and estimate it from there, because it may be that you just chose the wrong measurements. So in order to answer that question properly, you really have to optimize the experiment design specifically for that one parameter and then see with the best possible experiment design you can make, can you estimate it? And only if that fails can you rule out the possibility of being able to estimate that parameter. Turns out you can actually estimate it, although it's quite difficult. So that's one sort of utility of this kind of approach. And also, of course, as we've seen with the CT example, you can substantially improve the accuracy of parameter estimates or reduce the the requirements on the acquisition in experiments, and compared to an ad hoc design that just a machine operator might choose. The sorts of patterns that can come out of these optimizations are often not obvious at all, not the sort of thing that you would just choose naturally when you're setting up the machine. It'd be quite difficult to have intuitively selected those 4 clusters of CT measurements, for example. And of course, that optimization itself can actually give you new insight into the measurement strategy and even inspire new kinds of models that you might test.